Welcome everybody, this is part 4 in the 6th week of the Parallel Programming Concepts course. We now discussed different programming models, different parallelization strategies, design patterns, methodologies. So since we are now near the end of the overall course, we want to give you some interesting future trends in parallel computing. This is by far not a complete list, but this is a very subjective collection of the teaching team where we want to show you what seems to be interesting and relevant in the near future in the area of parallel programming. The first thing that is very crucial now and also in the future is the problem of the memory wall. So in week 1 we discussed a lot how the memory wall impacts our parallelization performance. You see this obviously in shared nothing systems too, but in shared memory systems this is a real issue, and with increasingly deep memory hierarchies in NUMA systems this becomes more and more important. So the hardware vendors, parallel hardware vendors, already identified this as a relevant thing. So they saw that the memory latency problem, the memory wall problem, that you can't access data fast enough in order to use all the cores in the system, that this must be solved somehow on the hardware level, because software can try to optimize, software can try to be cache aware, try to do local computation, but it only goes so far, and maybe there is a need for better hardware in terms of memory technology. And this is something which is actively going on and which is now at the beginning of 2014 a very relevant fresh topic. So we have a lot of innovation in memory technology that is going on now. One example is 3D NAND memory, where the hardware vendors basically do a rearrangement of memory hardware cells in order to stack more of them on each other. There's also the concept of a hybrid memory cube by Intel and other participants, where we have a 3D array of memory cells stacked on each other, and this stack is now put on top of the processor. They use an idea called through silicon via approach, TSV, which basically gives you the shortest possible path between the different cores and multiple layers of memory. And this is very fascinating because this will lead to the fact that we get amazingly fast, amazingly good memory performance in the future, even in comparison to current caching technology. So the interesting question here is, what will this future hardware trend do to parallel software development? Is something like PGAS maybe still a good idea? Do we really need that anymore? Do we need other approaches? Is data locality still important? So how does parallel software for these kind of memory systems look like? This is an open question, not answered so far. We're looking for prototypes of this technology, and then we will see how the parallel computing community will react on this trend. Another trend is ReRAM or RRAM. You may have also heard of the memristor idea by Hewlett-Packard, based on an old memristor theory concept. And the overall idea here is something that is called non-volatile memory. So we are looking into a future where memory will become non-volatile, so it will not forget its content after you switch off power. The interesting question again is, what does that mean for parallel computing? Is this relevant at all? Is this only an operating system problem? One interesting aspect here is that this non-volatile memory at the beginning will have worse performance than existing volatile memory technology. So can you somehow use the non-volatility example, for example, in the algorithm design in order to compensate for this particular problem? These are interesting memory hardware trends, and currently it's not clear what that will mean for parallel programming. A second thing that becomes more and more relevant, so it's not only a future trend, it's already started, is the so-called dark silicon problem. Dark silicon means that we now have processor technology which gets more and more cores from Moore's law, from the additional amount of transistors, but the power wall problem still exists. So we still have the capping and cooling capacity and all the other aspects we discussed in week 1. And the question is now, how can you even operate such a processor where the pure utilization of all transistors in terms of leakage will lead to a power consumption result that can't be handled by cooling and other aspects in the hardware? And the answer is dark silicon. Dark silicon means that at any point in time of the operation of the computer, only parts of the processor are working. These might be different parts, so you may have one part that is, for example, doing the floating point operations, or you have another part that is dealing with the processing of fixed number calculations. And the idea of dark silicon is now, or the investigation of the dark silicon problem is now, that these units cannot operate at the same time due to the power formula. So you need to find ways in order to use only parts of your multi-core processor at the time, but to do this in a very efficient way. So you want to drive this to the max. Currently, hardware vendors try to do this automatically. Intel has according technologies in their processors where they play with frequencies, so they can enable and disable higher or lower frequencies in different parts of the processor and do some dynamic scaling approaches there. Dark silicon expresses that this will go on. So this trend is already there, and it will continue like this. And if you have this, let's say, less homogeneous behavior of the computational units in your processor hardware, the question is, how do you reflect that in parallel programming? How do you deal with that in your code? How can you consider this? Is this even possible? Another trend that we see with the non-debatable hardware problems we still have is the idea of hardware-software co-design. So since the Powerwall problem and the dark silicon problem becomes worse, the new idea is, or one of the new ideas is to use the additional transistors from Moore's law for specialized logic. Partially this is already there with something like SSE or ILP mechanisms where parts of the processor hardware are focusing on specific problems in the overall execution of the instruction stream. But this goes beyond that because in these hardware-software co-design trends, we actually say that the application has a computational problem, a specific one, for example, encryption or hashing. And then the hardware should be built in a way that for this particular computational problem, there is special purposed hardware built inside the CPU. So our CPU becomes a collection of a general purpose part, which looks like before. But in addition, on the same die, we also have specialized co-processors, sub-processors that are very good in one or the other particular task. So you use the transistors for specialized hardware. And this gives you the advantage that you still get speed up because this particular computational problem is now problem solution is accelerated while not having the need to do this all in general purpose instructions. There is already an existing example for such a design, which is the cell processor. You can find this, for example, in PlayStation 3 consoles. And this thing has a 64-bit power core. This is the general purpose part, and 8 specialized coprocessors. And this is a trend which, from our point of view, seems to evolve. So future systems will have this kind of specialization inside the hardware. And the question again is now, how do you deal with that in software development? The typical trend is to have libraries that know how to utilize these coprocessors instead of writing the specific software for the specific coprocessors all the time by yourself. When you move now from future hardware trends to future software trends, there are interesting aspects which were, for example, identified by Jack Dongarra. He says that the efficient utilization of many core and hybrid hardware actually has a lot of implications on the parallel development. The first is that the classical, or let's say OpenIP idea of fork join parallelism may not really work in a heterogeneous environment. When we have hybrid hardware, we have the situation that our processing elements are no longer the same. So the idea of doing a fork join approach where you span a lot of more or less similar tasks, more or less equal size, and you put them on the different processing elements, this doesn't work if your processing elements do not act in the same way. So the programming model may now need to consider the heterogeneity or the potential heterogeneity of the underlying execution platform. How do you deal with that? The next point is that static partitioning of data, like in a structured grid approach when you think about the dwarfs, is something that may also not really work in hybrid environments. So you need more dynamic behavior in the data placement and in the data partitioning with respect to what is going on in your execution environment. Mixed precision is an interesting problem for computational sciences, where you may have the situation that you can reduce the computational load, serial computational load, by working with less precise numbers. This is also an interesting idea where you basically try to reach a numerical accuracy that is good enough. Not the best possible one, but one that is good enough. And by this, you spare some computational cycles or you spare some power cycles, and therefore you can increase the overall performance of your application. Another message from that you can typically find when the discussion of parallel programming in the future begins is that people can no longer deal with all that stuff. So the wish is that there is more support in terms of automatic procedures, self-tuning libraries, self-adapting software, so that software optimizes software and not the human programmer. In high-performance computing, especially in the Exascale project, which aims for the next generation of supercomputers, there is also a problem with fault tolerance. So when you have this increasing density of hardware being packed into a system, more memory, more transistors on the die, faults become more relevant. So in the, let's say, more far away future, we may have the situation that hardware fails more often, maybe only in tiny parts. And the question is, how do you deal with that? Is the software really prepared to have failing memory cells, flipped bits in the data, ill-formed control flows? The dependability research community has a lot of ideas there, also from traditional systems, but this is something that becomes relevant in the expectable future in the parallel computing environment, and the first people facing that are the high-performance computing people. And the next thing, or the overall recommendation for future software, is that we really need to think about algorithm classes in a better way. So it's not a good idea to start from scratch all the time and to do parallel programming from the very bottom up to the high level of the application algorithm, but we really need to have a better ecosystem of reusable parallel solutions so that you don't need to invest all the development effort for your particular problem. Some more specific trends, so what is expectable or what is already there and might be interesting. OpenMP version 4 is an interesting thing. In OpenMP version 4, you can see that hybrid computing starts to sneak into all the programming models. So in OpenMP 4, we have SIMD extensions so that you can directly target SIMD hardware, for example, in your processor, but still have the abstract programming model. They also have a concept of targeting extensions and device data environments. So the OpenMP4 standard considers the existence of accelerators, for example, of GPU hardware, in addition to the CPU, and tries to give you a programming model that allows you to facilitate both the accelerator hardware and the CPU hardware inside of the same application. A similar approach of thinking is happening in the OpenACC stack. OpenACC is a standard that aims for developing something like an OpenMP for accelerators. This is, for example, also supported by NVIDIA, so it's a serious project with existing implementations. It looks quite similar to OpenMP, so you have annotations in C and C++ and Fortran. And the code you get out may also run on the accelerator directly. So this is also worthwhile a look. There are nice implementations, for example, for Xeon Phi, and this may help you in writing your application in a way that it's future-proof, so it can be ported to existing fresh hardware, parallel hardware, and maybe upcoming new classes of hardware. A more fancy idea is the autotuners idea. Autotuning means that you take a particular parallel code and you make it configurable. So you may, as a very easy example, for example, have a particular variable that allows you to tweak the granularity of your tasks or to work on the data decomposition factor or things like this. So we have these variables or these knobs to twist inside your software, but you have no clue what the right setup is for a particular execution environment. And in practice, people often simply try that out. They sit down and run it in this or that configuration, measure the performance and see what works in the best way. And autotuners simply are the idea to take this task and automate it. So an autotuner library is taking your implementation, it takes the different compiler switches and your different application knobs, and then tries out all the different variations and gives you afterwards the result of what works in the best way for this particular execution environment. Research results, scientific publications show promising results, especially in linear algebra software. There's an implementation called Atlas, which works with this approach. So this is a trend that we expect to become even more relevant in the future, that software stacks are able to tune themselves for a particular execution environment so that the human developer or the DevOps person is not in the need of doing this in a manual fashion. And the last level of abstraction, or the final level of abstraction, is something like the Intel Math Kernel library, where you get high-level abstract functionality, for example, math functionality, which typically can be linked to one or another dwarf, as we discussed in the last unit. And you get this functionality from the hardware vendor or from a specialized software vendor, and you just use it. So you don't think about how parallelization works inside. You just assume that the library is written by smart people and they know how to do this, so they either use the SIMD extensions of the compiler and the hardware, or they do some kind of task parallelism, and you really don't care, because what you want to have solved is your math problem, and by using this library you get the best possible performance on a particular piece of hardware. The advantage is this takes a lot of burden from you, so it relieves you from the burden of parallel programming. The disadvantage is that this is typically only working with particular hardware pieces, with chosen hardware where the library is optimized for. So Intel is very good in this business, and you have to decide now if this is worth the investment and effort or not. So in sum, we have the situation in parallel computing and parallel programming that there are future trends. There's active research in next generation hardware, and this is driven by the supercomputing community, but also by the non-debatable fact that computing moves from desktop systems to mobile systems. In mobile systems, we have the power consumption as a really crucial issue. So how do you can write performant code, for example, based on accelerators and mobile phones, while considering the power problems you have in these devices. Power wall and memory wall are identified and well known, so the hardware people try to come up with new ideas. And this leads to the fact that the world of parallel hardware will become more heterogeneous, more hybrid. So we have different things combined into the systems, and hybrid computing, how we call it, is the future default from our point of view. So when you do parallel programming, you will have now and in the future the situation that you not have a homogeneous execution platform as we are used to, like a UMA SMP system, but you have a wide mixture of accelerator hardware and capabilities of the cores, memory hierarchies and all these things. So homogeneous memory, flat memory, constant access times, this is history, and we need to deal with that. And the computer science community and also the industry is constantly producing now new proposals for programming paradigms and languages and libraries, and hopefully we are able to give you in this course an overview of what is going on at the moment. And our understanding is that this trend will continue, so you need to keep attention and try to figure out what is going on and how do these trends can be linked to what we saw, for example, in this course here.